Hey there, Seahawks. It's Miss Adams, and in this video, we're going to learn about linear regression inference. All right, so a linear regression t-test. We want to test if there is an association between two quantitative variables, x and y. We look at a sample of data on a scatter plot and estimate the true association of the population's plot. All right, the least squares regression line for our sample is y hat equals a plus bx, where b is r, the correlation coefficient, times the standard deviation of y divided by the standard deviation of x, and a equals y bar, the sample mean for y, minus b, my slope, times x bar, my sample mean for x. The population model that we don't know is y equals beta sub o plus beta sub x plus epsilon EI. So really, we don't care too much about the epsilon. Those are the errors. We're not going to get too far into that in this course. So A is beta sub O or alpha, and that's our y-intercept. B is beta, and our slope. All right, our residuals or our errors are independent and normally distributed. This is normal with a mean of 0 and a standard deviation that's equal to the standard error of our residuals. So small residuals, let's say our standard error is 2 versus our standard error of 10. So you can just kind of see what those differences would look like in your scatter plot. All right, a t-test. So we're testing the slope of the population regression line. So state our null hypothesis would be beta is equal to 0, which means there is no linear association between x and y. And our alternative would be beta is less than, greater than, or not equal to 0. Either there's a positive slope, negative slope, or it's just not equal to 0. Our conditions. So our conditions are a little bit different for a linear regression t-test or t-interval. So we need to have linear data. So you're going to sketch a scatter plot that's linear with no outliers. They need to be independent. So each piece of data can be assumed independent of the other. This would also be your 10% rule. Normal residual. So the residual plot of, or a normal probability plot of the residuals is linear. You need to have equal variance. So the residual plot shows no change in spread of the residuals. And then it needs to be random. It either needs to be stated or assumed. If those conditions are met, then we can use a t-distribution and do a linear regression t-test. All right, so I do like to try to remember these conditions by the acronym LINER, L-I-N-E-R. All right, so do our test statistic is a t. So t is equal to our statistic minus our parameter divided by the standard deviation of our statistic or the standard error. So our statistic is b, the sample slope, minus beta, which is usually 0. Over the standard error of our slopes. So it's just b divided by the standard error of our slopes. Our p-value is the probability of getting our test statistic, something less than or greater than our test statistics. T-CDF if you already know the t-value. Otherwise, your calculator will do it when you do the entire test. And degrees of freedom here is n minus 2 because I'm working with 2 quantitative variables. All right, our conclusion will be 3 sentences. So it's either going to be we reject or we fail to reject the null hypothesis. We have sufficient or insufficient evidence that the slope of the population regression line is less than, greater than, or not equal to 0. And then thus, as whatever increases, the alternative decreases or increases, the slope is changing, right? So, if x increases, y increases. If x increases, y decreases. And as x increases, y changes. So these are just kind of what your scatter plots would look like if we're doing a greater than, less than, or not equal to test. So the changes could be either or. All right, our confidence interval is b plus or minus t star times the standard error of our slope. So again, b is our slope. Our sentence would be, we are blank % confident that the interval from blank to blank captures the true slope of the population least squares regression line for whatever your y variable is and your x variable. Make sure you put it in context. So An example, assume we are told that a 95% confidence interval for the slopes is 0.05435 to 0.1804. This is from airlines data. So we are 95% confident that as the distance increases by 1 mile, the airfare increases by $0.05435 to $0.1804. All right, and then the mechanics of the test, so you can, with the actual data or with a computer output, you're going to have two options. A lot of times this will be with a computer output, so you need to be able to read the important parts there. Up at the top, our response attribute, that's our y variable. The one under your constant or intercept is going to be labeled either constant or intercept, will be your x variable. You have a and b as the coefficients. A is your y-intercept, b is your slope, so the y-intercept one's going to be with the constant, and the slope is going to be with your x variable. We don't really need any of those values. We don't ever use the adjusted r-squared. We do use r-squared, just not adjusted. And then s, the standard deviation of your residuals is SE, or of your errors, I'm sorry. SEB is the standard error of your slopes, and then T, your test statistic, and then P, your p-value. And that's pretty much everything. And then here you have your equation. So they wrote out the least squares regression line equation for you. So the predicted age of the wife is 1.574 plus 0.9112 times the age of the husband. All right, our test statistic formula here, we'd get 35.249. All right, so if we plugged in B and beta is going to be 0, and then the standard error of the slopes, we can get our test statistic. And so then there we can get our p-value by plugging in the test statistic and doing a TCDF. And we get about 0, or we can just look at it from the table. So they told us that the p-value is 0.0000, basically 0. All right. Does a relationship exist between high school GPA and freshman year performance in college? A random sample of 40 freshmen at a local college was taken, and their high school GPA and GPA from their first full year were recorded. All right. So my hypotheses, N is 40, degrees of freedom is 38. We're going to do a test here. So my hypothesis would be that beta, the population slope, is equal to 0. The alternative would be that beta is not equal to 0. They didn't really say, they just said, does a relationship exist? So I don't know if it's supposed to be higher, greater in college, or less in college, what? So we're going to go with the not equal to. Here is everything that they're giving us for this problem. So they've given us a computer output, the normal probability plot of the residuals, a scatter plot of the original data, a residual plot. So we have a whole bunch of stuff that we're going to use to check the conditions here. All right, so here's all our important pieces from that computer output. So we're going to do the test. So state, plan, do, conclude for a test. Beta is the true slope of the population's least squares regression line for first year GPA and high school GPA. Our null hypothesis is beta equals 0, and our alternative is beta does not equal 0. Degrees of freedom is 40 minus 2, so 38. When we're checking the conditions, we're going to use the acronym LINER. So L stands for linear. The scatter plot is approximately linear with no outliers. I is independent. We're going to check the 10% condition. 40 is less than 1/10 of all students, so independence is assumed. N is normal. A normal probability plot is approximately linear, so normal residuals are assumed. E is equal variance. The residual plot shows similar variability for each x value, and then R is random. Random sample was stated. All right, so my conditions were met, and I'm going to be doing a linear regression t-test. My test statistic formula. When I plug in numbers, I'm pulling these off of my computer output. We get a test statistic. I didn't actually calculate it. I just looked at my computer output. T equals this value. I'm going to draw my normal curve. This is a t distribution with 38 degrees of freedom. I'm going to go to 0. I'm going to go to my test statistic. Because I'm doing a not equal to test, I'm going to do negative 5.3 and positive 5.3, my test statistic on both sides. And my p-value is basically 0. Remember, from 5 standard deviations out, I'm really not going to have much in the way of shading there. All right, and our conclusion would be we reject the null hypothesis because our p-value is less than alpha. We have sufficient evidence that the slope of the population regression line is not 0. Therefore, as high school GPA increases, the first-year college GPA changes. All right, and then we're going to also do an interval with this same data set. So state our parameter has not changed. We're doing a 95% confidence interval, and degrees of freedom is 38. Conditions were met before. We're going to do a linear regression t interval. So our formula is our statistic plus or minus our critical value times the standard error of our statistic. Our statistic is all about slopes here, so b plus or minus t star times SEB. B plus or minus t star. So I'm going to do inverse t, 38 degrees of freedom, and get t star there. The area, if we're doing 95%, that leaves us with 5%, and on one tail, that would just be 2.5%. So for area, I'd put in 0.025. For degrees of freedom, I'd put in 38. And then the standard error of our slopes, I got from my computer output, and we get this interval 0.6763 to 1.5043. So we are 95% confident that for every increase of 1 point in high school GPA, the first year GPA increases between 0.6763 points and 1.5043 points. All right, go Seahawks.